Great, thank you very much. Yeah, great pleasure to kick this off. I hope I can string together a sequence of very controversial statements that can then lead up to an exciting discussion. Um, so these are my co-authors, as you can see, and in particular, there are some people who are more in the machine learning world, but we also have Michael Kuczynski, who's a psychometrician, and who helped us understand the idea of how to measure intelligence, which is the topic of this work. So the basic idea here is that this insight that once you can measure something, then you can improve on it, then you can control it. And so the idea behind this work is that we would like to find ways of measuring the intelligence of crowdsourcing systems, because then we may be able to improve them, and we may be able to do so in a controlled fashion with a feedback loop, because we can measure how intelligent they actually are. Why is this important? Well, there are a lot of hybrid systems now that consist of human intelligence and computational intelligence that play together. And while this might seem like a science fiction thing, there are in fact already a lot of systems that work this way. Think of recommender systems, or think of a search engine where there are human relevance judgments, where people click and put the intelligence of their judgment of what the right answer should be into that click, which can then be used by machine learning algorithms to improve the search engine. So this is a very real scenario. And we were wondering, how can we measure the actual intelligence of groups, of crowds of people? And what we fell back to was the idea of, how do you measure individual IQs? You use IQ tests, right? And for example, we use the Raven standard progressive matrices, which is a standard IQ test which has been shown to be predictive for a lot of interesting intelligence-related tasks. And you can see here an example. I hope you don't get too distracted by trying to figure out what the right answer is. I can assure you it's from the very beginning of the test. So what we get then typically are these normalized scores. On the left-hand side, you see the number of correct responses, the distribution over the population of people. On the right-hand side, you see that normalized into an IQ score. And the basic thing you need to know about these things is that they're normalized such that 100 is the mean and a standard deviation is 15. And those will serve as reference points later on. Now, this is how you measure the intelligence of an individual. Now, how do you measure the intelligence of a group? And the idea here is, and this is kind of the simplest starting point, is that we can do majority voting on the answers. So suppose you have all of these people, the rows here, taking the test, the columns are the questions, and they choose different answers for these IQ questions. And then we can do a majority vote, just look at which choice has been made the most by the participants. That then is the majority IQ test, so to speak, and we can score it, and in this way we can determine what the aggregate intelligence of this group is in this very limited kind of majority sense. But this already gives some interesting results, and there are basically two interesting reference points. You'd like to know if this aggregated IQ is higher than the average IQ in the group from which it is built, and if it is higher than the highest IQ of members in that group. If you first focus on the plot at the bottom right, this is for the entire data set, and you can see that if you take the full spectrum of people, then as you increase the crowd size, which is plotted on the x-axis here, the IQ does go up considerably, way above the average, because it goes up to 125, 130 there. But it doesn't quite reach the intelligence of the most intelligent member, which is signified by the green line in the bottom right corner. However, if you take a more constrained sample of people with IQs, say, in the top left between 95 and 105, so a very homogeneous crowd, then the aggregate intelligence, which you see here in the red line, or with the special algorithm in the blue line, will be much above the intelligence of the most intelligent individual, which is this line here, by definition here, 105. So by the simple majority aggregation, you do get substantial gains in IQ as measured in this way. Now, you can also define what we call the contextual IQ, which is the idea of figuring out for a given crowd if you add a particular person to that crowd, how much value do they actually add? And what we show here is on the x-axis the actual IQ score of a person, and on the y-axis what we call this contextual IQ. And you can see, of course, someone who is more intelligent will have a higher contextual IQ. It is value for the group, but it's not a simple correlation. So you can see that there are people, say, who have a certain IQ of 100 who can contribute in very different ways, even negatively, to the group IQ. And so in this way, you could use such a measure to compose teams of people who would do particularly well together. Now, we applied this to very concrete crowdsourcing example. And so here you see the front page of Amazon Mechanical Turk, the thing that they term artificial intelligence. And of course, for such systems, it would be great if we had some way of measuring how intelligent they are, how good they are at completing certain tasks as a function of different parameters such as payment, how many people we use, what kind of reputation we require from them. And this crowd IQ methodology allows us to do exactly that, and in this way figure out how to optimally set those parameters. Of course, under the assumption that IQ is a good surrogate measurement for the ability of the crowd, which may not be the case for all tasks. I'll show you a couple of examples. On the left-hand side, you see the crowd IQ on the y-axis and the worker's reputation on the x-axis. You know that on Amazon Mechanical Turk, you can filter on the worker's reputation, which is basically the rejection, the acceptance rate that they have for the tasks that they submit. And quite intuitively, if you only let the most reliable people complete your tasks, your crowd IQ will be highest. And as you allow more less reliable people, it will go down. So this is a rather intuitive result. Now you also see here how the IQ behaves as a number of the crowd size. And you can see that the more workers you have on your task, the higher the aggregate intelligence will be. But it kind of flattens off, so you have diminishing returns there. And if you're particularly smart and in your choice of which question to present next and do some kind of active learning, then you can do even better and achieve higher intelligence with fewer workers. Now here's another plot which I think is particularly interesting. Here you see how different incentives come into play to determine intelligence. On the left-hand side, we have two different modes. We either don't say that we will reject any tasks. So there's no threat to the worker. They can just complete it and nothing will happen. On the right-hand side, we threatened in the task description that if they got it wrong, we would reject that task. In the end, we didn't do that because we wanted to pay them because they actually contributed to the study. But they were under the impression that they could be punished, so to speak, by a rejection, which would hurt their reputation. And you can see through self-selection then, the IQ goes up to an enormous level of 137, because only those people who think they're good at answering these tasks, or in particular this task, will actually answer, and so we get very high quality in comparison to the case where there is no such threat. Of course, you need more time. What the red line here indicates is the IQ score per minute, so to speak. And so since there will be fewer people answering your task or working on your task, you will make slower progress in solving your task. On the right-hand side, you see a similar plot, but this time on the x-axis you see the reward per task. And each task here is basically one IQ question, right? And so the interesting thing here is that if you pay too little, the IQ will be low, but also if you pay too much, the IQ will be relatively low. And this is because if you pay too much, more spammers come into the system and will spoil your result. Just to conclude, my hypothesis entering this discussion is that we need to be able to measure the intelligence, or in some sense, ability of crowdsourcing system in order to make them better and control them. Thanks.